Hello, everyone. Today we will be starting the first chapter of our Klein textbook, which basically gives an introduction to organic chemistry and reviews some of the more important concepts from general chemistry that will pertain to what we will talk about for the next year. Okay, so what is organic chemistry? Now, the word organic is often used colloquially to refer to like food that's grown without pesticides or something being more natural in general. All right. But from a chemistry perspective, when we discuss organic chemistry, what we're referring to is the study of carbon containing molecules and their reactions. Okay. When a molecule undergoes a chemical reaction, two things need to happen. First, the molecules need to collide. They need to bump into each other. Second, bonds are going to be broken and new bonds are going to be formed. So why do chemical reactions occur? Well, there's several reasons, and we will be discussing them over the course of the next year. Okay, but one thing you want to start keeping in mind right now is that we are going to be focusing on the electrons of the molecule, okay, because that is really where the action is happening. Okay, so why do we spend an entire year talking about organic chemistry? Okay, well, you may be familiar with the phrase carbon is the backbone of life. Or you may have heard that we are what is referred to as carbon-based organisms. Both of these are very true, okay? Organic compounds are generally thought of as compounds containing carbon or compounds that contain carbon-hydrogen bonds. There are some examples of carbon-containing compounds that are not considered organic, such as salts, okay? So, as you can see, down here, okay, we can convert ammonium cyanate, which is an inorganic salt, even though it contains carbon, it's still considered inorganic, into the organic compound urea through heating it, okay? Many living things, especially, us humans, are composed of a carbon backbone, meaning that our biomolecules have carbon as the backbone of being put together, okay? What this also means for us is that we need a source of carbon so that we can rebuild our biomolecules. You can rebuild your DNA and you can rebuild your proteins when you need to. Humans get their source of carbon from food, okay? Many pharmaceutical and like clothings and plastics also contain carbon backbone. So that is why we're spending so much time talking specifically about the chemistry. Okay, so it was relatively speaking recently in the mid 1800s when it was first suggested that substances are defined by a specific arrangement of atoms. Okay, that is to say that for any specific molecule, the atoms are connected together in a very specific way. Molecular formula alone, that's not adequate to define molecules because it's only like a listing of the atoms that are in the molecule. It gives us no identifiable information about how those atoms are arranged. So compounds that have the same molecular formula but they're arranged differently are called constitutional isomers. And you should remember that phrase from general chemistry. Okay, so while organic chemistry does focus on carbon as the backbone of organic molecules, there are going to be other atoms that are involved in bonding to carbon. Atoms that are most commonly bonded to carbon are going to include nitrogen, oxygen, hydrogen, and the halides. Okay, now with some exceptions, each element generally forms a very specific number of bonds with other atoms. For carbon, we can see it's 4 bonds. For nitrogen, nitrogen forms 3 bonds, oxygen 2, and then hydrogen and the halogens, just 1. So a covalent bond is a pair of electrons shared between two atoms. And when we say covalent bonds, we indicate that they are equally shared between both of those two atoms, okay? So for an example, let's look at a bond between two hydrogens, okay? Now, remember, how does potential energy and stability, how do these two relate? Lower energy means a compound is more stable. So we can look at the distance between the two hydrogen atoms and find out what is the optimum stability, okay? And that is the bond length, okay? What forces keep the bonds at optimal length? Well, we've got a couple things going on when we have a bond. Attractive forces between something that is positively charged, like the nuclei, and the negatively charged electrons. Repulsive forces between positively charged nuclei, as well as repulsive forces between the negatively charged electrons. So to understand the different types of bonds that we're going to see in organic chemistry, it's important to go back to the basics and review the structure of an atom, okay? So again, we remember protons, positively charged, reside in the nucleus. Neutrons, negatively charged. They are also in the nucleus. Electrons, negatively charged, they reside in orbitals outside of the nucleus, right? Valence electrons are the electrons that are in the outermost shell, right? So if you recall, when we are putting electrons around a molecule, we've got the shells that indicate the distance from the nucleus, and then the orbitals that indicate the shape, okay? Valence electrons are in the outermost shell. They can be in more than one orbital, all right? And that's what we're going to be focusing on because it's those valence electrons that are involved in bonding. Okay, now you can always calculate the number of valence electrons by analyzing the electron configuration of an atom, but for group A elements only, which fortunately is actually what we'll be dealing with in organic chemistry, you can just look at the group number on the periodic table and that will tell you the number of valence electrons that atom has. So if we look at carbon, for example, carbon is in group 4A, it has 4 valence electrons. Okay, so drawing Lewis structures. We can use information regarding an atom's valence electrons to draw the Lewis structure of a molecule. So for simple Lewis structures, simply draw the atoms out with their appropriate valence electron number around them, then put the atoms together so that they share pairs of electrons to make complete octets. Okay, if you can see that we're working largely with the atoms in organic chemistry in the second row, they want to have 8 electrons around them. Okay, we are also working with hydrogen, which will obviously not have 8 electrons around it, which is fine because it only needs to be sharing 2. Okay, so let's look at this example down here. We're looking at NH3. How do we put it together? Okay, we can see from the periodic table that nitrogen has 5 electrons around it. It's in group 5A. Okay, now 3 of those electrons are unpaired. Hydrogen is in group 1A. It's got 1 electron. So I can simply pair up the 3 hydrogens with the 3 unpaired electrons of nitrogen to draw the Lewis structure of my NH3 molecule. Okay, so for simple Lewis structures, you simply draw the individual atoms using the dots to represent valence electrons, and then put them together so you make a complete octet around that second row element. Okay, we'll be looking at other forms of drawing in the next chapter. Okay, see you soon.